Every second, our sun unleashes more energy than humanity has used in its entire history. All the power plants, all the engines, all the lights that have ever shone on Earth are just a whisper compared to the sun's continuous, thunderous roar. The sun's secret? Nuclear fusion, a process that forges new elements and releases the fundamental energy of the universe. At its core, fusion is about bringing things together. On the sun, hydrogen nuclei are forced together under immense pressure and heat. When they fuse, they form helium and release a tremendous amount of energy, the same energy that warms your face on a sunny day. Imagine the sun's core over 15 million degrees Celsius, 250 billion times Earth's pressure. Here, hydrogen atoms become a superheated plasma, zipping around and colliding. Most of the time they bounce off each other, but sometimes, two nuclei fuse, unlocking the energy that powers our world. The light and heat from the sun, all born from fusion, travel 93 million miles to Earth, nourishing life and driving our civilization. The sun's fusion reactor is the ultimate source of almost all energy on Earth. It dictates our weather, grows our food, and has inspired wonder in humanity since we first looked up at the sky. Understanding fusion is about understanding the engine of life itself, and perhaps, the key to our future. Fusion is the cosmic engine that makes life possible. And now, we're trying to bring that power down to Earth. Stars are the universe's grand alchemists, turning simple hydrogen into the building blocks of planets, and us. After the Big Bang, the universe was mostly hydrogen and a bit of helium. Everything else, the carbon in our bodies, the oxygen we breathe, was forged in stars through fusion. In the sun, the main process is the proton-proton chain. Two protons fuse, one becomes a neutron, forming deuterium. Deuterium fuses with another proton, creating helium-3 and releasing a burst of energy as a gamma ray. Two helium-3 nuclei then fuse to make helium-4, the same helium in party balloons, and release two protons to start the cycle again. This chain reaction, happening countless times every second, keeps the sun stable, balancing gravity's pull with fusion's push. The magic is in the mass. The final helium nucleus is slightly lighter than the hydrogen that formed it. That missing mass is converted directly into energy, as Einstein described, E equals mc squared. Even a tiny bit of mass, when converted, creates a spectacular amount of energy. This is how stars shine, and how they make life possible. Fusion is the universe's way of turning matter into light, and it's the process we hope to harness for our own future. The word nuclear often brings to mind fission, the process powering today's nuclear plants. Fission splits heavy atoms like uranium, releasing energy but also long-lived radioactive waste. Fusion, by contrast, squeezes light atoms together, producing energy and harmless helium as ash. Fission's fuel, uranium, is finite and must be mined. Fusion's fuel, hydrogen, is abundant, with deuterium easily extracted from seawater. A gallon of seawater contains enough deuterium to match the energy of 300 gallons of gasoline. Fusion is often called the holy grail of energy, immense power, minimal waste, and inherent safety. If a fusion reactor loses control, the reaction simply stops. It's a star that can be turned off. That's why fusion could change everything. For decades, scientists have tried to replicate the sun's power here on Earth. We can't use gravity like the sun, so we use extreme heat over 100 million degrees Celsius to get atoms moving fast enough to fuse. The leading design is the tokamak, a giant hollow donut where hydrogen gas is heated into plasma and caged by powerful magnetic fields. No material can touch this plasma, so magnets keep it suspended in a ring. The world's largest fusion experiment, ITER, is being built in France by 35 nations, aiming to prove fusion can produce more energy than it consumes. ITER won't power cities, but it's the crucial step toward real fusion power plants. Other approaches use lasers to compress and heat fuel, like at the National Ignition Facility in California. All these efforts are part of a global race to unlock fusion's promise. Each experiment brings us closer to harnessing a star's power. The dream-clean, limitless energy for all. The path to fusion energy is tough, requiring new materials' precise control and self-sustaining reactions. The main challenge is ignition, making fusion reactions produce more energy than they consume. We must hold superhot plasma steady and develop materials that survive intense neutron bombardment. But the rewards would be transformative. virtually limitless clean energy, with no greenhouse gases or long-lived radioactive waste. Fusion fuel comes from water available to all nations, potentially ending energy conflicts. Recent breakthroughs have brought new optimism, like the National Ignition Facility, producing more energy from fusion than the lasers used to start it. Private companies are accelerating progress with innovative designs. We're closer than ever to making fusion a reality. The quest for fusion is about more than energy. It's about reaching for the stars with our ingenuity. The dawn of the fusion age is on the horizon,